Okay, now that we know something about how we measure concentration, we can start to talk about acids, bases, and pH. Now, you've probably heard of pH before, even if it's only on deodorant commercials. But pH is really just the concentration of H plus or hydrogen ions in a solution. The pH scale, at least in living things, goes from 0 to 14. 7, which is right in the middle, is what we consider neutral, and it's the same pH as a pure glass of water. Anything that's below 7 on the pH scale is considered acidic. The further we get from 7, or the lower the pH number, the more acidic it becomes, or the more concentrated the number of hydrogen ions. Anything above 7 on the pH scale is basic. And the further we get from 7, or the higher the pH number, the more basic it becomes, or the lower the concentration of hydrogen ions. Now, hydrogen ions is a lot of syllables to say over and over, and H plus is kind of annoying too. So H plus are called protons, and the reason they're called protons is because that's what they are. It's not just a cute nickname. If we look at hydrogen on the periodic table, we can see that it has an atomic number of 1, atomic mass of 1, so no neutrons, and because atoms have to be neutral, it's going to have 1 electron. So hydrogen is 1 proton and 1 electron. Now, if we want to make this positively charged, a cation, then we have to get rid of an electron. And when we get rid of hydrogen's electron, all that's left is a proton. So H plus or hydrogen ions are called protons. Now, let's take a look at how pH is calculated. I know this looks like a lot of numbers, but I'm going to walk you through it and you're going to see it really does make sense. The equation for calculating pH is this. pH is equal to the negative log, which is short for logarithm, of the concentration of protons. Anytime you see something in square brackets like this, it means the concentration of whatever is inside the brackets. So this bracket, H plus bracket, means the concentration of H plus or protons. Now, logarithms, other than just being a button on your calculator that you probably never use, are really just a shortcut. So let me show you what that means. If I have a 0.01 molar, so that means 0.01 moles per liter of hydrogen ions, then the pH of that is 2. And the reason, or how we know this, other than like doing the math class to figure out what a logarithm is we just move the decimal place until we get to a number that is not a decimal number, till we get to a whole number. So if I have to move the decimal 1, 2 places so that I have the number 1 instead of a fraction of 1. And because I moved it 2 places, this is a pH of 2. For this one, I have 0.00000001 molar protons in solution. And in order to get to this 1, I have to move the decimal 7 times. Therefore, I have a pH of 7. Here, I have to move the decimal place 13, or the decimal 13 places in order to get to a whole number. So that means that I have a pH of 13. Now, if you look at this, this is the most concentrated solution, but it has the lowest number. This is the least concentrated solution, but it has the highest number. This can be a little confusing when you're going back and forth between talking about the concentration of protons and the pH. So, it's important to remember that pH and proton concentration are inversely related. That means they're opposites. So, an acidic solution has a high concentration of protons and a low pH. A basic solution has a low concentration of protons and a high pH. Now, let's talk about what we mean when we say acids and bases. Now, chemists have a number of different ways of defining acids and bases, but the one that we're going to use is that acids are what we call proton donors, right? They're donating their proton to the solution. That means that when you put an acid, so this is an acid, hydrochloric acid, the stuff that's made in your stomach, when you put this in a solution of water or a container of water, the water separates the ions, just like we talked about before, and now we have H plus and Cl minus. And look at that, a proton just appeared. So that means that this is an acid. So water separates the H plus, and the Cl minus, and that's what allows this proton to suddenly appear and be part of the concentration of protons in that solution. Bases, on the other hand, are what we call proton acceptors, or you could think of them as proton thieves. So that means that when you put a base, this is sodium hydroxide, or also known as lye. When you put a base in water, the water again separates the ions into sodium and its anion, which is called hydroxide. Now, this hydroxide, looks around and it's like, oh, look at that. There's a proton. I'm feeling the attraction here. We got negative, we got positive. So as soon as hydroxide shows up, it grabs a proton and the two of them combine to form water. The proton disappeared. Therefore, this must be a base. Now, the pH of our body is tightly regulated. It's not the same throughout our body. So different compartments have different pHs that they have to remain at in order for the things in that compartment to function. If the pH becomes too acidic or too basic, it can cause proteins to unfold and stop working. Or it can cause an ion imbalance between the inside of the cell and the outside of the cell that can make your muscles either spasm, stay contracted, or be paralyzed, not contract at all. The same thing can happen with your nerves. So keeping the pH stable is very important. So to keep the pH stable, we have in our body a number of what we call buffers. Buffers act like chemical sponges to keep the pH stable. So just like you would use a sponge in the kitchen, if it's dry and there's water on the countertop, you use the sponge to soak up the extra water. But if you need water somewhere, you can take that wet sponge and squeeze it and the water will come out. Same thing in the chemistry of our body compartments. When there are too many protons in a body compartment, the buffer can soak up those protons and keep them from affecting the pH. Okay? When there are not enough protons in the solution, the buffer squeezes like a sponge and the protons are released again to bring the pH back to where it should be. So, what we can say is that buffers help us to stabilize the pH. If we look at the pH as we add drops of acid to it, an ordinary beaker of water would start at pH 7 because it's neutral. But as soon as we add 1 drop of acid, hydrochloric acid, for instance, the pH will drop dramatically. We add a second, it drops even further. And then it just becomes pure acid. Okay? However, if we have a buffer in that beaker of water, when we add 1 drop of acid, the pH doesn't change. Another, and another, and another. Again, the pH doesn't change. Of course, just like sponges can only soak up so much water, or you can only wring out so much water from a wet sponge, there comes a point where the buffer becomes saturated. It can't soak up any more protons. And at that point, only at that point, does the pH begin to drop as we add acid. Another thing to know about buffers is that they aren't all set for a neutral pH. There are compartments of our body that are maintained at a higher or a lower pH, and they have special buffers that can keep them there. So, this is a buffer that's good at maintaining things at around a pH of 10. So, we add acid, nothing changes, and then finally we've reached the capacity of the buffer and the pH starts to go down.